Hello, everyone. Good afternoon, good morning, or good evening from wherever you are right now. Thank you for joining today's webinar. My name is Jesus. I'm one of the members of ISCFD, and I'm very grateful to have you today here. The talk is delivered to you by the International Society for Computational Fluid Dynamics, ICFD for short. The ICFD is run by a dedicated team of like-minded volunteers, such as myself or our founder, Nathan Savasky, among others, who aim to increase the visibility of CFD research. Our purpose is to bring people and ideas together by creating opportunities for knowledge exchange, such as this webinar. We regularly host CFD professionals from varying backgrounds to share their work and perspectives. If you like the idea and format, we invite you to follow us on LinkedIn, Twitter, and our recent official website for any updates. Also, there are some past events on our YouTube channel that you can check out, so please feel free to check them out later. Today's event is expected to last about an hour, with 40 minutes of the talk itself and 15 minutes of the Q&A. If you have any questions, please feel free to post it in the chat. I collect them and read them out loud at the end of the talk for you. Today, we have the chance and the pleasure to meet and listen to Dr. Joseph Nagy, CEO of Eulerian Solutions. Dr. Nagy completed his PhD in compressible multiphase flows at Vienna University of Technology. Later on, he further pursued a postdoc at Johannes Kepler University, where he focused on polymer materials. He is currently the chairman of the Technical Committee for Tutorials and Documentation and the chief editor of the recent OpenFOAM Journal. You may also know him for his YouTube channel, where he helps the community with insightful tutorials about CFD with OpenFOAM. We are happy to have you here today, Dr. Nagy. Without further ado, the floor is yours.
Thank you very much for your kind words. Again, am I audible? Just one.
Yeah, we can
very
hear
good.
You loud and clear.
Okay, then let me just share my screen. Can you see it?
Yep.
Okay, very good. Then I will start my talk. Okay, so welcome everyone. I am glad that I am able to talk in front of this crowd. Thank you very much for the organizers to invite me. I'm very happy to join this event and talk about my impressions, my experience with the open source CFD code OpenFOAM. I'm not sure how many of you are familiar with OpenFOAM. Do you work with OpenFOAM or with other tools? But I will focus on my personal journey with OpenFOAM, which started approximately 13 years ago. So I will talk about a little bit, I will do a short introduction to my person and to OpenFOAM, and then I just want to show you results from my journey with OpenFOAM throughout the years, starting with my PhD, then my postdoc, and then my current results as from my consulting company. So my name is Dr. Josef Nagy. I studied in Vienna physics, and I did my PhD at the Institute for Chemical Engineering. So, and this is where I really started with CFD, and especially CFD with OpenFOAM. And then during my postdoc, I continued with OpenFOAM, and now in my company, I also use this open source tool. And I'm also, I'm trying to be active in the community. I am the chair, as was mentioned, of the Committee for Documentation and Tutorials in the governance system of OpenFOAM. Charlie Mockett is also in the crowd. He's also a chair of the turbulence committee. So I try to be active in the community, and I personally initiated the tutorial collection at wiki.openfoam.com, which is a collection of OpenFOAM tutorials to help newcomers get into OpenFOAM. And also I'm one of the initiators of the new OpenFOAM Journal at journal.openfoam.com, and I'm going to talk about that also at the end of my talk. You may know my YouTube channel, hopefully, possibly. It has been around now for years. It has over 2 million views in those years. There are over 18,000 subscribers, and it gets approximately 1,000 views every day. So I'm very happy that people use it, that there is a need for help during the startup period when you learn OpenFOAM before you can start your own CFD projects. And I try to be active in the community and contribute back in every possible way. Although I'm now working in industrial projects, so there is less time for such things, but I still try to take time and contribute back to the community. And in my company, I focus on providing custom CFD solutions to customers, model implementation, workflows, testing, validation. And of course, I offered on-site training before COVID, which now was moved to online training. But yeah, that's how things work nowadays. So a short introduction to OpenFOAM, if you don't know what OpenFOAM is. Now, OpenFOAM is not one software like you would consider AutoCAD to be a software where you click something and then a GUI comes up, or Microsoft Word, or just Notepad++. OpenFOAM is, if you take it seriously, is actually foam, which is a namespace, a dialect of C++, with a wide collection of two things. First, applications and libraries. And these applications can be then executed in a terminal, and with them you can pre-process your CFD simulations or post-process them, or they can also solve your simulations. And these applications are called solvers. They solve partial differential equations for many small volumes for the mesh, and there are a lot of these applications, and there is a very good reason for that. Because what we want to avoid with OpenFOAM is to carry around all the available models and libraries, and you want to only load those models in form of libraries which are required for your physics. So I like to compare these applications to knives of a chef, because a chef also takes different kinds of knives to cut a fish or a meat or vegetables and so on. So you have to know what kind of physics you want to solve, and according to that you select your solver, your application, which only loads the models that you require to solve your problem. So OpenFOAM is really just a large collection of libraries and applications, and one of the major points here is that you can also create your own applications, and you have a lot of power to tweak around with the numeric settings, with meshes, with boundary conditions. So it is a very powerful tool. But on the other hand, you also have to know what you are doing. So it is considered to be an expert tool, and especially at the beginning when you're a newcomer start, this learning curve is very steep. So this is why I personally initiated, and also why others also joined the technical committee for tutorials and documentations to help newcomers overcome this initial very steep learning curve into this expert tool. Yeah, just a quick, if you don't know OpenFOAM, an OpenFOAM simulation case is not a file or a file container. It is just a normal folder on your hard drive, which consists of at least 3 subfolders: 0, constant, and system. And in 0 are your initial and boundary conditions. In constant are, for example, your material properties or your mesh. And in system, you have your simulation settings. And when I say you have your initial and boundary conditions, I mean you have so-called dictionaries, which are simple plain text files, and you have to set them up correctly. And then your application, your solver reads them in, the input that you provide, and also during simulation, the solver writes out text files. And you can visualize them in different kinds of visualization tools. Most people use ParaView for that. OpenFOAM is free to download and also free to use. It is open source under GPL version 3, and there are different versions of OpenFOAM for openfoam.com, openfoam.org, and Foam Extend. I don't want to go into more detail about those topics, but just to mention that there are different versions. And now I would like to give you a short summary of my group of Professor Michael Harasek, who enabled me this possibility to start with OpenFOAM back then with OpenFOAM version 1.7. So it was a very old version back then. I analyzed and I created a custom solver for multiphase compressible fluids for the droplet breakup in an asymmetric flow. And this was very important because we were dealing with an industrial project with the injection of heavy oil into a furnace. And it is impossible to do experiments in the steel industry in such a furnace. So simulations were the only way to understand the processes in the furnace. And in order to verify the solver, we did some experiments and simulations. And so here you can see the basic idea. So in literature, you can find, or at least when I did that, you could find a lot of information about the breakup of droplets in a symmetric or a uniform flow. So if you take a look at the flow here in the top, you have your droplet, and then the air is moving around your liquid droplet symmetrically. But what we are interested in is an asymmetric flow. What happens to the droplet when the high velocity airflow only touches one side? So for the literature, problem for low viscosities, you could estimate that for a certain Weber number, for a lower Weber number, you will have so-called Rayleigh-Taylor piercing, which means that your droplet will be flattened and then after a while pierce through the center. And for very high Weber numbers, you have shear-induced entrainment, which means that the airflow will shear off layers of your fluid as it is rushing by. And the Weber number, if you don't know, is the ratio of inertia to surface tension. So the higher the velocity, the higher the Weber number is. So the higher your velocity, the more likely it is that the shear-induced entrainment happens. And the Ohnesorge number is a ratio between viscosity and inertia and surface tension. So the higher the Ohnesorge number is, the higher your viscosity is. And then in this publication by Theophanos, they showed these curves, these blue, red, and brown curves that for very low viscosities, this rough estimation of 100 and 1000 as this transition region between the two breakup models is valid. But if you increase the viscosity of the liquid, then these regions will change and will be moved to higher Weber numbers. And then there is a region where no breakup occurs, then the Rayleigh-Taylor piercing, and then the shear-induced entrainment. And what I started with is doing experiments and simulations with glycerin and ethanol and see whether the simulation model predicts the same droplet breakup as the experiments do. So if we consider now glycerin with a very low velocity of 25 meters per second coming out of a nozzle here from the left-hand side in the simulation, and the same in the experiments on the right-hand side, yeah, the quality of the experiments are poor, just given by the equipment that I had available at the university. But you can see that there is a glycerin droplet dropping onto this airflow here. And then what happens that it is flattened a little bit, but no droplet occurs. So indeed, the simulation delivers these results that no breakup occurs. Now, if you, instead of having glycerin, you use ethanol, so the viscosity is a lot lower, then these curves will assume that the Rayleigh-Taylor piercing will happen. And indeed, both in the experiments and the simulation, what happens is that the moment the droplet reaches this free jet, it is flattened, and then after a while, it is pierced in the shear region. And this is also, you can kind of see it here if you know what you're looking at. So there are two white dots, which are the edges of this of the hole of the center of the droplet. So also in this case, the simulation in this asymmetric flow will give you the same phenomenon. And for a very high velocity, so instead of a maximum value of here 25 meters per second, if we assume 160 meters per second of the velocity, then what will happen is both in the experiments and the simulation that the droplet falls onto this free jet, and then the free jet shears away the droplet layer by layer. So also in this case, the phenomena, the droplet phenomena is correctly described. And then if you are interested in more detail, just take a look at my PhD thesis. I found additional regions in this Ohnesorge-Weber number diagram. So take a look at my PhD thesis if you're interested in more detail. Because after my PhD, I was fortunate enough to have a postdoc position at the Johannes Kepler University in the group of Professor Georg Steinbichler at the Institute for Polymer Injection Molding. And there I was, my focus was on injection molding simulations with OpenFOAM, so creating a custom solver for that. And polymer injection molding is a very common technique to create plastic parts in the communication industry, medicine industry, automotive, packaging industry. And it is a very challenging process because the pressure in the process are very high, multiple hundreds and thousands of bar. The viscosity is very high. It is a non-Newtonian fluid. You have very high forces, and it is difficult to do experiments. It's not impossible, but very difficult. And simulations are a good alternative to experiments. And I did a lot of talks about that, so maybe you already saw that. I will just take out one of the results there. So if you're not familiar with the injection molding process, it consists of 5 steps. So first, in the plastification step, you have a screw which rotates, and due to shearing and also external heating, the polymer pellets are melted, and then molten plastic is collected in front of the screw, and then this liquid polymer is in the second filling phase being injected into a mold, which has the shape of your final product, the negative shape of your final product. And then this is the liquid polymer is injected into the mold. Then in the packing stage, additional pressure is applied in order to fill the last parts of the cavity. Then the part is being cooled down, and then it is ejected. And I concentrated mostly on the injection part because this is the most challenging part of the process. So the fluid flow is a multiphase flow. It is compressible. The equation F state is a very complex polymeric model, the so-called Tate model. In the energy equation, you have shear heating, heat transfer from melt into the mold, and you have a non-Newtonian fluid. So it is a very complex phenomenon. And I was very happy that then that the simulation worked and delivered reasonable results, not only for simple geometries, but also, for example, for this real life application case, which is an end plate to an electronic equipment. So what's happening here? So through this rod, the polymer melt is injected, and then there is this small bridge between the rod and the actual end plate part. And the idea between the small bridge is that after ejection, you can just break off the injection rod, and then you end up with your only the end plate that you will use, and then you can put in screws through these holes and then screw the end plate to the rest of the equipment. And what we did here, we injected in experiments this rather complex geometry, and we also ran simulations and then compared the pressure value, the injection pressure values between experiments and simulations. And what is very, very interesting, that the characteristic times when this rod is being filled and this bridge is being filled, and also and the pressure increases while this rod is being filled, then this bridge is being filled, and then you have a smaller increasing pressures while the actual end plate is being filled. So the increase in pressure is correctly depicted in the simulations, and then also the time when the mold is filled is depicted correctly. So the simulation can deliver the same results as experiments, and in simulations you can also test out extreme conditions that you don't want to test in a real life application because you destroy your machine. So, okay, so that was just a short summary of my postdoc. And then, as I mentioned, I started with my own company. And at the beginning, one of the major focus that I was working on were fire safety simulations, together with Tian Building Engineering from Singapore, especially with Dr. Alex Lee. And fire safety is a very important issue, especially for building engineers, because you cannot really build a building and burn it down just to test whether your fire safety ideas were good enough and then rebuild the building. So simulations are the only or one of the few possibilities to evaluate fire hazards in a building that has to be built, has to be constructed. So, and the thing is that because it's an engineering task and not an academic task, so the simulation has to be run within a reasonable time of a couple of hours overnight or maybe over the weekend, but you cannot run simulations for months in this regard. They also gave talks about that, so maybe you already know these results. But in the first step, we verified the possibilities in OpenFOAM with verification and validation case coming from Mr. Steckler from, I believe, the 70s, where he built a small room. You can imagine here this orange box is as a room, and here on one side you have one door. And what Mr. Steckler did, he placed a methane burner in the center of this room. He switched on the methane burner, and then he measured the temperature in the center of the room. And then you can use this as a validation case for CFD, because then you can just burn methane in the center of the room and then take a look at the temperatures in the door. This is what we did with different approaches, with the 4 most commonly used combustion models that are available in OpenFOAM. Here you can see a slice through the center of this room. So this exact slice that you can see here, I show the mesh on. And what happens also in real life is that the flame will lean towards the back wall. So here you have the back wall, and on the left-hand side, you have the door, the open door. And what you see is that cold, fresh air is being sucked in by the flame, and hot air is leaving the room in the top. And then there is a transition region where the hot and the cold air change. But qualitatively, all the 4 models deliver the same results. And if you now compare the temperature values in the door, so in the bottom you have very low temperature values, and as you increase, then you reach a certain point where then the temperature all of a sudden increases. And this is also what you see here. So this is the height of the door, and at the beginning you have very low values, so the ambient air, fresh air, and then the temperatures increase. And you can see that there are some deviations between the black curve, the experimental curve from Mr. Steckler from the 70s, and simulation results in OpenFOAM. So the first four are the four different combustion models. So the temperatures are above the measured values, and in several simulation attempts, we found out why these models overestimate the temperature. So the first of a lot of ideas was to just leave away the combustion models in OpenFOAM and just define via FV options a heat source. So no combustion, just the same heat source, and then take a look at the temperature evolution, and you get the same temperature evolution, but the temperature is a bit lower, so there is some numeric errors in those models, which are given by the fact that you are using runs models and possibly also mesh resolution issues. And then a second and a larger influence of error is if you use conjugate heat transfer in your simulations, which means that you introduce a wall, the actual wall, so you allow a heat flux through the walls, because in these simulations the walls are assumed to be adiabatic, and then this heat flux through the walls will also additionally lower your temperatures and come to the actual experimental values. And so the position of this transition region is still a bit off, but this is something that can be managed with different turbulence models. Okay, and then you can utilize these experiences in a real life application. For example, here we took a look at a car park with a lot of cars, supply air, exhaust air, and also jet fans. And then what you can do, you can take a look at the velocity fields. You can switch on, switch off a jet fan. So for example, these two are switched off, and then these three are switched on. In the center, we placed a fire, a typical fire that you would have, for example, if a motorcycle starts burning. And then, so here is the fire location. And then from the combustion models, you can calculate the soot release rate, and from the soot release rate, you can calculate the so-called visibility. So here, black is bad visibility, gray is good visibility. So here you can see a cut through the Y normal cut here, so where the fire is located. So you can see that at the top of the building, after 50 seconds, visibility is very low due to soot production, and especially in regions where the jet fans are switched off, their visibility is low, as you would expect, but the simulations are showing exactly that. And in regions where the jet fans are operating, their visibility is still maintained after a certain time. And with this, you can run simulations how much time people have to leave this car park if a fire occurs. Then another short project that I was working on are rain runoff simulations, which is a 2.5D simulation model. So it's a modified shallow water equations where you calculate the height of the water on roofs. And it is more a decision-making tool for building engineers to know in which direction rain will run off the roofs of their buildings. But it is a very cool and handy tool because it's a very fast tool. So within a couple of minutes, you have a transient simulation of your problem. So as a verification case, I thought about this inverted roof, because if rain falls onto that inverted roof, all the rain will be collected in the center. And then indeed, after a while, the water is collected in the center. So in the first step, there was no rain, only an initial water layer that was collected in the center, and then I switched on rain as well, and then the same happened. And here I show you the mean. So if you integrate over the entire roof, then without rain, the curve, the mean height remains constant, which means that the equations are solved correctly. And then if you switch on a rain with a certain rain intensity, then there is a linear increase of rain quantity on that inverted roof. So here nothing is leaving the roof. Then a more closer real-life application with a fancier roof here shows you that if you have rain, or very large rain, which is the maximum value that was recorded in Singapore, you can see that here you have rather large thickness of water height, and also in the bottom, in some parts, the water is collected. In other regions, it is only running off. If you only take 1/10 or 10% of this extreme rain, then you can see that here the water runs off and is not collected, but in the other parts of this roof, water is indeed collected. So this is a very handy and fast tool to make these decisions where your water will run off your building, and you can then reshape your roof so that water is collected in regions that you want it to be collected. And then as the last major CFD topic that I was working on in the last couple of years were aneurysm simulations, so brain aneurysm simulations, actual fluid structure interaction simulations with my previous university, but now as an external company with the group of Professor Mayor. And here we got angiogram measurement data, so CT scans of actual real life aneurysms, brain aneurysms, and then we set up the simulations and we also validated the simulations with experiments. But here I want to talk about aneurysm simulations, and then because we wanted to understand the behavior of aneurysms, and maybe we can learn something about the rupture of aneurysms and also the onset of aneurysms. And for that, we took a look at, we assumed the blood vessel walls to be linear, but also, as you can see here in the measurement data of the university, they showed that the material properties of the blood vessels in the brain are non-linear. So here you can see the strain and stress curve. So you can assume it to be linear, but after a certain strain, you will be off with your linear model. As the driving force, of course, you take the blood pressure. From literature, we know that in the brain, there is a certain curve depending on whether you have a hypertensive blood pressure or the normal blood pressure. Here, I will show you the results with the hypertension, so the worst case scenario. And then you can give this pressure curve on the inlet and then see what happens, how the blood vessel behaves under these pressure loads. And what we are taking a look at is aneurysm onset. So we run the simulations with the actual aneurysm, and what happens if we cut it away manually, and then compare with the linear elastic and the non-linear elastic models, the displacement of the wall shear stress in the fluid, and the actual the stresses in the solid wall. And these are important points because especially the wall shear stress is considered to be one of the major quantities that you can use to understand brain aneurysms. So here you can see on the top, on the left hand, let's just start on the left hand side, you have two models with the linear elastic models, and on the right hand side, the non-linear elastic material models, and on the top, without the actual aneurysm, and on the bottom with the aneurysm. And here you can see the wall shear stress, and you can see that here the aneurysm grows in a region of low wall shear stress. And some authors in literature say that this is indeed this way, that low wall shear stress regions are where usually aneurysms grow. Others say that it's high wall shear stress regions. So in this case, the first assumption seems to be correct. But what is more interesting here is that the stresses in the wall, if you clip the stress values at 100 kilopascal in the wall, you can see that this red region, so the area of high stresses in the walls, are being reduced by the growth of this aneurysm. So, and we assume that rupture will occur around 400 and 500 kilopascal. So it's still off from that region, but it is not far away. So here, what we can see that the body sees that it is being stressed in this region on an everyday basis, so that it starts to develop an aneurysm to lower the stress in the blood vessel. So this seems to be the driving force in this case. Now, if you take a look at a second patient with a smaller aneurysm, and you cut away this aneurysm and then compare the stresses, here what you can see that in this case, all of a sudden, due to the growth of the aneurysm, the stress is indeed increased. However, the stress without aneurysm was at 20 kilopascal, so far away from 400 and 500, and it is only increased until 40 or 50 kilopascal, so still far away. But the wall shear stress seems to be decreased. So in this case, it seems that the body tries to decrease the wall shear stress by the growth of this aneurysm, because it can allow itself to increase the stresses in the walls, because it is still far away from this rupture region. So very interesting results, and now we are planning to, or actually we already submitted a research project on this, where we want to further investigate and help our local physicians with CFD simulations to understand their patients better. And now, as a last topic, because we are running out of time now soon, I want to talk about my community work regarding the tutorials and also the new OpenFOAM journal. So as I mentioned, I was the initiator of the tutorial collection on wiki.openfoam.com/tutorials, which was a pilot project for the technical committees in the steering committee framework of OpenFOAM, and I am very happy that now it has a sustainable operation. It has been now around for approximately 5 years, and the main goal is to provide newcomers up-to-date tutorials to the latest, and up-to-date means to the latest or second latest versions of OpenFOAM. So both the OpenCFD version, the foundation version, and possibly also the foam extend version. And currently there are over 100 up-to-date tutorials in the collection. So there is a large collection that people can go to and search through. So these are my colleagues who help and maintain the tutorial collection and also add new tutorials. And our responsibility is to maintain so that there is a high quality of the tutorials, and also that they are always up to date. That is not just a wide collection of all tutorials. And this is also what I mean by sustainable, that it kind of came to a stage where the people are always coming and contributing new. So some people are leaving, but others are coming. There are new tutorials coming in. Some tutorials are outdated, but there is always a constant number of tutorials, so newcomers can start with their own CFD projects. And we have different series there. So for example, if you just want to have a first glimpse of OpenFOAM, you have a collection of 4 tutorials, which will give you within an afternoon, for example, a very good idea about the workflow of OpenFOAM and what you can do with OpenFOAM and with what you cannot do with OpenFOAM. It can be completed within a couple of hours. If you want to learn OpenFOAM in more details, we have the 3-week series for you, where we have 1 week, the basic week, where you learn about the basics of OpenFOAM, then a more advanced week where you learn about more advanced topics. And then we have dedicated programming week for OpenFOAM, because yes, in OpenFOAM you can program your own models, and you can just go to the 3-week series and start by clicking on day 1 and just start to learn. If you are interested in certain topics, for example, turbulence modeling, we also have we collected or organized the tutorials by topics, so you can just then go through the turbulence tutorials if you're interested. We have also a collection by contributors. So if you like the style of one of the contributors, you can go through their tutorials. So if you're interested, go to wiki.openfoam.com/tutorials. So here you have the full path. And if you want to contribute, just contact us at wiki@openfoam.com and we will help you set up a tutorial page if you think that you have a tutorial that would be beneficial to the community. Now, the newer development is the OpenFOAM Journal, which we started a bit more than a year ago. And the idea behind the OpenFOAM Journal was that you have conferences, physics-related conferences on, for example, multiphase physics and journals on multiphase physics. But on the conference side, you had OpenFOAM-related conferences, like the OpenFOAM conference and the OpenFOAM workshop, where you could present your OpenFOAM-specific topics, but there was no real journal in these well-established journals. You were able to publish, but it was difficult to publish really the code implementation part of your problems, because they are only interested in the physics, not in the numerical details. So there was a clear need to also launch a journal where you can focus only on the OpenFOAM related part of your research. So if you ask yourself, why should I waste my research in a new journal when I could just submit my results in a well-established journal, then please go ahead, submit your paper to a well-established journal, concentrating on the physics, but you can write now a second paper where you focus on the numeric implementation with which then you created exactly those physical results. So it's not that you have to waste your paper in this journal, but you can write an additional paper, which then underlies the equations that you show in your well-established journal. So it is really an additional possibility to publish more of your results. So you can go to journal.openfoam.com and then take a look at the homepage. It is an initiative of the technical committee for documentation and tutorials, and it is backed and supported by the steering committee. And there are two major keystones of the OpenFOAM Journal, and I am one of the chief editors, two chief editors there. We focus on reproducibility of the results and the benefit for the OpenFOAM community. So we encourage people to submit source code if they implemented source code, and also use cases where people can reproduce their results in the manuscript. So that people can just compile the source code and then run these cases, and then from that reproduce the results and then start their own projects from there. So the key points is that it's free to publish and also free to access. So you can just go there and download the PDFs. We just started, so there are, do I have a couple of, yes, so here we have 900 registered users. Currently, there are 5 papers online. I think there are 4 published and 1 is in post-production, so should be finished soon. And which is a large milestone for us, because now we can apply for DOI as well as an ISSN number. You need 5 publications to do that. And then the next milestone is going to be next year in 2023, when we will be able to apply for indexing, for example, for an impact factor and indexing in, for example, Scopus. So this is our goal where we want to go. Currently, we are not allowed because the journal has not been around for long enough, but we are working on that. There are already 5 papers accepted, 21 are under revision, so there are a lot more to come. So I can encourage all of you to submit papers to the OpenFOAM Journal, especially because we place such an importance on reproducibility and the benefit to the community. And in order to cover small sponsorships, small costs, like, for example, applying for ISSN number and DOI, there is a small fee that you have to pay. So that is covered by sponsorships by the two very kind companies, Compute and Upstream CFD. Thank you very much to them for their support. And yes, I forgot that you can also store auxiliary data, so also large cases, and we store the large cases on Dataverse. So people can also submit cases with multiple gigabytes of data. So actual real life application data. Yeah, and we have an editorial board, an international editorial board from industry and academia, and we have an additional larger editorial advisory board from all over the world who support us with reviews and also give us feedback on the operation of the journal. So yeah, that was it. That was my talk. I hope that I could motivate you to work with OpenFOAM, and I hope that you could see some of the highlights of my journey with OpenFOAM in the last 13 years.